In this video, we invite you to follow a single raw material, fresh sugarcane, on its entire journey from green stalk in the field to pure white crystal. Over the next few minutes, you'll step inside a modern cane sugar factory, see how thousands of tons of cane are handled every day, and watch how chemistry, heat, pressure, and precision machinery work together to create the refined sugar you use at home. We begin in the cane fields, where the story of sugar actually starts. Rows of tall sugarcane are planted in straight lines, each stalk similar in height, thickness, and maturity. This uniformity is no accident. It is the result of careful variety selection, planting, fertilizing, and farming practices designed to supply the factory with consistent raw material. Technicians walk through the rows, inspecting stalks, checking firmness and ripeness, and cutting sample pieces to confirm juice quality before harvest begins. Once the cane is ready, harvesting teams and specialized machinery move in. Mechanical harvesters or coordinated cutting crews slice the cane close to the ground, remove the leafy tops, and cut the stalks into manageable sections. These pieces, called billets, fall in clean, ordered layers and are loaded directly into trucks or trailers positioned alongside the harvester. In the truck, the open cut ends reveal fresh, moist fiber, and the load is visually inspected for uniformity and cleanliness. When the truck is full, it is tagged as a distinct lot and leaves the field. Approaching the gate, each one passes through security and enters the weighing station. At the weighbridge, the gross weight of truck plus cane is recorded, providing the basis for yield calculations and payment to growers. Inside the control cabin, operators use computer systems to match weights, lot tags, and supplier information. Once weighed, the trucks are directed to the raw material reception area. Unloading is the first dynamic step inside the factory. At the reception station, hydraulic platforms or tipplers lift the truck body, allowing the cane to slide out under its own weight into large steel hoppers. The cane falls across heavy grates that stop oversized debris, then lands in vibrating feeders that shake it loose and spread it evenly. From there, the cane flows onto wide intake conveyors that carry it steadily into the preparation line. Alongside the belts, operators monitor flow, clear any jams, and ensure that the feed to the next section remains continuous and uniform. Before extraction, the cane must be cleaned and conditioned. On the washing section, powerful sprays of water hit the cane as it travels along the conveyor, washing off soil, dust, and loose fragments. Wastewater drains away through dedicated channels to treatment systems, while the cleaner stalks move forward. Next, the cane passes through chopping machines that cut it into shorter pieces. and then into shredders whose rotating knives and hammers tear the cane into a loose, fibrous mat. This step is critical. By increasing the surface area of the cane fibers, it greatly improves the efficiency of juice extraction in the mills. The heart of the mechanical process is the crushing station. The prepared cane mat enters a series of heavy-duty milling units, each one made up of large steel rollers turning under immense pressure. As the mat passes between these rollers, the fibers are compressed and the juice is squeezed out. Between milling stages, the partially extracted cane may be sprayed with water or recycled juice to wash out additional sugar. Underneath the mills, stainless steel troughs collect the warm, golden brown sugarcane juice and channel it into the juice handling system. At the same time, the spent fiber, called bagasse, emerges drier and more compact, ready to be carried away on its own conveyor network to be used as boiler fuel or treated as a byproduct. The fresh juice, however, still contains many non-sugar components: fine fibers, soil particles, natural pigments, and soluble impurities. In the juice treatment area, it is first screened to remove larger solids and then pumped through heaters to raise its temperature. Carefully dosed chemicals such as lime are added to adjust pH and encourage impurities to coagulate. The treated juice then flows into clarifier vessels, where slow movement and gravity allow heavier particles to settle and lighter froths to rise. Skimming devices remove floating scum from the surface, while clarified juice overflows from the middle zone into collection channels. From there, it may be passed through further filtration systems, such as filter presses, to polish the clarity and remove remaining suspended solids. Throughout these stages, the laboratory plays a vital role. Samples are taken at key points: raw juice, clarified juice, syrup, and final sugar, and brought to a dedicated quality control lab. Here, technicians measure parameters such as sugar content, bricks, color, turbidity, pH, and ash. Using instruments like refractometers, colorimeters, and spectrophotometers, they compare results with strict process specifications. If any value drifts outside its allowed range, process conditions can be adjusted in real time. Only when the clarified juice meets defined quality criteria is it allowed to continue to the next major transformation, evaporation. In the evaporation station, the aim is to remove water and concentrate the juice into thick syrup. Multi-effect evaporators, tall cylindrical vessels linked in series, use steam on one side of heat exchange surfaces and boiling juice on the other. By operating under partial vacuum and reusing vapor energy from one effect to the next, these systems extract water efficiently. As the juice moves from effect to effect, its solids content rises and its behavior changes from a liquid to a viscous syrup. Sight glasses and instruments allow operators to monitor temperatures, pressures, and levels. The product leaving the last evaporator is a rich amber cane syrup with a high sugar concentration, ready to form crystals. Crystallization takes place in large vacuum pans, which are essentially controlled reactors for crystal growth. Hot syrup is introduced into the pan and boiled under vacuum until it becomes supersaturated, holding more dissolved sugar than it can permanently keep in liquid form. At this point, tiny seed crystals are introduced or allowed to form, and the dissolved sugar begins to deposit onto their surfaces. By carefully adjusting evaporation rate, temperature, and vacuum, operators control how fast the crystals grow and what size they reach. Inside the pan, the mixture, called masse cuite, is a thick slurry of sugar crystals suspended in mothered liquor. When the targeted crystal size distribution is achieved, the masse cuite is discharged and guided toward the centrifuges. Centrifuges perform the physical separation between solid sugar crystals and liquid molasses. Batches of masse cuite enter perforated rotating baskets. As the baskets spin at high speed, the heavy molasses is forced outward through the perforations, while the crystals remain against the inner wall. Water or steam washes may be applied to rinse off the last traces of molasses. When the cycle is complete, the centrifuge slows and the damp pale sugar is discharged onto conveyors. The separated molasses, rich in non-crystallized sugars and colorants, is collected for further use or sale as a byproduct. The damp sugar must then be dried and cooled to become free-flowing refined sugar. It is carried into a fluidized bed dryer, where a carefully controlled stream of warm air passes up through a moving bed of crystals. The air lifts and agitates the grains, evaporating remaining surface moisture. Afterwards, the sugar travels over cooling conveyors and through screening machines that classify it into standard product and off-size fractions. Oversized crystals may be remelted or reprocessed. Fines are collected separately. The main fraction, standard refined sugar, then flows into storage silos. Inside these silos, sugar behaves almost like a liquid, pouring in from above and forming shifting piles while level sensors monitor inventory. From the silos, the refined sugar is fed by gravity and controlled feeders into packaging lines. Depending on the product format, it may be packed into small retail bags, larger food service packs, or industrial sacks. Automated systems open empty packages, fill them with accurately weighed doses of sugar, and seal them by heat or stitching. Inline check weighers verify that each unit is within tolerance. Inspection devices ensure seal quality and outer appearance. Faulty packages are automatically rejected. Good packages continue down the line to be grouped, stacked on pallets, and wrapped for stability. At the end of the packaging haul, forklifts or automated vehicles transfer finished pallets into the warehouse. In the warehouse, refined sugar waits in neat labeled stacks, ready to be shipped. Inventory systems track which pallets belong to which production batches, maintaining full traceability back through the process, and ultimately to the cane fields. When customer orders arrive, pallets are selected, moved to the loading docks, and placed into trucks or containers. Doors close, security seals are applied, and the vehicles leave the factory, carrying refined cane sugar to distributors, manufacturers, stores, and, finally, to consumers.